Okay, for chapter 14, we will be discussing heat and heat transfer methods. Now that we've gone over temperature and some of the units involving that, we're able to talk about more specifically heat and the different changes and phases between cooling and heating certain objects or liquids up. So here we'll go over heat, defining it, the temperature change and heat capacity, phase changes and latent heat transfer methods, conduction, convection, and radiation. So for heat, in chapter 7, we define work as force times distance and learned that work done on an object changes its kinetic energy. We also saw in chapter 13 that temperature is proportional to the average kinetic energy of atoms and molecules. We say that a thermal system has a certain internal energy. Its internal energy is higher if its temperature is higher. If two objects at different temperatures are brought in contact with each other, energy is transferred from the hotter to the colder object until equilibrium is reached and the bodies reach thermal equilibrium, or they are at the same temperature. No work is done by either object because no force acts through a distance. The transfer of energy is caused by the temperature difference and ceases once the temperatures are equal. These observations lead to the following definition of heat, which is heat is the spontaneous transfer of energy due to a temperature difference. So in this figure, for A, the soft drink and the ice have different temperatures, T1 and T2, and are not at equilibrium in the figure. For B, when the soft drink and ice are allowed to interact, energy is transferred until they reach the same temperature, T prime, achieving equilibrium. Heat transfer occurs due to the difference in temperatures. In fact, since the soft drink and ice are both in contact with the surrounding air and bench, the equilibrium temperature will also be the same for both. So just because they make contact right here, once those temperatures are the same, that's when they reach equilibrium. Owing to the fact that heat is a form of energy, it has a SI unit of joules. The calories, cal, is a common unit of energy defined as the energy needed to change the temperature from 1 gram of water by 1 degree Celsius, specifically between 14.5 degrees Celsius and 15.5 degrees Celsius, since there is a slight change temperature dependence. Perhaps the most common unit of heat is the kilocalorie, kcal, which is the energy needed to change the temperature of 1 kilogram of water by 1 degree Celsius. Since mass is most often specified in kilograms, kilocalorie is commonly used. Food calories, given the notation cal with a capital C, and sometimes called big calorie, are actually kilocalories, but here it's 1 kilocalorie equals 1,000 calories, a fact that not easily determined from packaged labeling. It is also possible to change the temperature of a substance by doing work. Work can transfer energy into or out of a system. This realization helped establish the fact that heat is a form of energy. James Prescott Joule performed many experiments to establish the mechanical equivalent of heat, which is the work needed to produce the same effects as heat transfer. In terms of the units used two two terms, the best modern value for this equivalence is 1 kilocalorie equals 4,186 joules. So there's a conversion between kilocalories and joules here. So here you see that heat is a form of energy, and so that's why we're able to incorporate that with some of those energy factors that we learned earlier. So now we go into heat capacity. One of the major effects of heat transfer is the temperature change. Heating increases the temperature while cooling decreases it. We assume that there is no phase change and that no work is done on or by the system. Experiments show that the transfer heat depends on three factors: the change in temperature, the mass of the system, and the substance and phase of the phase of the substance. The dependence on temperature change and mass are easily understood. The internal energy of a system is proportional to the absolute temperature and the number of atoms or molecules, and therefore the mass. The transferred heat also depends on the substance, so that, for example, The heat necessary to raise the temperature is less for alcohol than for water. For the same substance, the transferred heat also depends on the phase. So it depends if it's a gas, liquid, or solid. So down here we have our equation for heat transfer. You have Q equals, well, your Q is your heat transfer, your M is your mass, your change in T is the change in temperature, and your C is your specific heat. And that depends on each material and each phase. So your specific heat is going to be different if you have a solid, liquid, or gas, and also it depends on what the material you're using. So if you have like water, H2O, if you have a solid, which is ice cubes or something like that, that'll be different from the liquid form of it and from the gas form of it. So in figure 14.4, we have the heat Q transferred to cause a temperature change depends on the magnitude of the temperature change, the mass of the system, and the substance and phase involved. So here we're adding Q, temperature change, or heat transfer, to here, and then afterwards it's going to be double what the heat transfer was. So for A, the amount of heat transferred is directly proportional to the temperature change. To double the temperature change of a mass M, you need to add twice the heat. So here, because it's twice the heat, we have twice the temperature change. Obviously, we can't add mass to just one object unless we're adding a different object to it. So the only thing that can really change here is the temperature. For B, the amount of heat transfer is also directly proportional to the mass. So if we're adding mass to one object or another, then yes, it would be a direct proportion to heat. The amount for C, the amount of heat transfer depends on the substance and its phase. If it takes an amount Q of heat to cause a temperature change delta T in a given mass of copper, it will take 10.8 times that amount of heat to cause the equivalent temperature change in the same mass of water, assuming no phase change in either substance. So here we're adding heat to this copper, and then if we're trying to add the same amount of heat to the water, we'd have to have this variable here because the specific heat for water is different from the specific heat of copper. So even though the masses might be the same and the temperature change might be the same, that specific heat will be different. For example, 14.1, you have a 0.5 kilogram aluminum pan on a stove is used to heat 0.25 liters of water from 20 degrees C to 80 degrees C. How much heat is required? What percentage of the heat is used to raise the temperature of the pan for B and C for the water? So here we're given our specific heats for water and specific heat for the aluminum. Okay, so first we need to figure out the temperature difference. So we have our 80 final, 20 initial. That gives us a change of 60 degrees Celsius. We must calculate the mass of the water. We know the mass of the water is 1,000 kilograms per meters cubed. 1 liter of water has a mass of 1 kilogram, and that the mass of 0.25 liters of water would be 0.25 kilograms. So we're able to just get that from that density. For 3, we calculate the heat transferred of the water for the specific heat, which was given to us here. You can get it from table 14.1 as well. We have Q equals mc delta T, and we know our mass, 0.25 kilograms. We know our specific heat, 4,186, and we know our change of temperature. So 60. You multiply that out, you get 62.8 kilojoules. So for 4, you calculate the heat transfer of the aluminum as well. Same thing, same equation. You have 0.5 kilograms. Our specific heat given here and from the table 14.1 is 900. And same change in temperature. So here we get 27 times 10 to the 4th joules. So 27 kilojoules. So compare these two, and you add both of them together. You'll get the total heat transfer. And so if we're trying to find out what percentage of the heat came from the pan and what percentage came from the water, you will do that specific heat, the 62.8 kilojoules for the water over the total, times the percentage. So that'll give you 69.9. And then you'll do the same thing for the pan, the 27 over 89.8 times 100%, and that'll give you 30.1%. And that's the differences. That's the differences in percentages from where the heat came from. Okay, so for example, 14.2, truck brakes used to control speed on a downhill run do work, converting gravitational potential energy into increased internal energy, higher temperature of brake material. This conversion prevents the gravitational potential energy from being converted into kinetic energy of the truck. So here, calculate the temperature increase of 100 kilograms of brake material with an average specific heat of 800 joules per kilogram times degree C. So we have our specific heat there. That's our C, is our M. If the material retains the energy from a 10,000 kilogram truck descending 75 meters in a vertical displacement at a constant speed. One down there. So our strategy here is if the brakes are not applied, gravitational potential energy is converted into kinetic energy. This is something we learned back in chapter 7. When brakes are applied, gravitational potential energy is converted into internal energy of the brake material. We first calculate the gravitational potential energy, mgh, that the entire truck loses in its descent, and then find the temperature increase produced in the brake material alone. So here we use mgh of the total truck, so that's 10,000 kilograms times 9.8, which is g, times your height. Remember, they mentioned in the problem, this is all vertical displacement, so we don't have to have any components here. So that gives us 7.35 times 10 to the 6 joules. So now here it says calculate the temperature from the heat transferred using Q equals mgh, and delta T equals Q over mc, where m is the mass of the brake material. So here we have delta T, we have our Q. Remember, Q is energy. So if this is the entire energy that you would get from the gravitational potential energy, that should be also the energy that you could potentially get from any heat transfer. So here we have our mass difference would be 100 kilograms, because it says calculate the temperature increase of 100 kilograms of brake material. So we have our M is different from the one up here. We're using the heat transfer that should equal our gravitational potential energy as well. And we know our specific heat, 800 joules per kilogram times degree C. So you put all that together and you get 92 degrees Celsius. That's the temperature of the brake material on a descending truck. So it gets pretty hot up there. Okay, for example, 14.3. Suppose you pour 0.25 kilograms of 20 degrees C water, about a cup, into a 0.5 kilogram aluminum pan on the stove, off the stove with a temperature of 150 degrees C. Assume that the pan is placed on an insulated pad and that a negligible amount of water boils off. What is the temperature when the water and the pan reach thermal equilibrium a short time later? Okay, so the strategy here. So a pan is placed on an insulated pad, so that means little heat transfer occurs with its surroundings. If it's insulated, all that heat's basically going to be trapped in there. Originally, the pan and the water are not at thermal equilibrium. The pan is at a higher temperature than the water. The pan's at 150 degrees C, and the water's at 20. Heat transfer then restores thermal equilibrium once the water and the pan are in contact. Because heat transfer between the pan and the water takes place rapidly, the mass of the evaporated water is negligible, as mentioned in the problem, and the magnitude of the heat lost by the pan is equal to the heat gained by the water. The exchange of heat stops once the thermal equilibrium between the pan and the water is achieved. So the heat exchange can be written as the absolute value of the Q hot equals Q cold. This is where they would be at equilibrium. So we know that Q equals MC delta T. And so we have Q hot because the aluminum is hot, right? So we're going to use the mass of the aluminum, the specific heat of the aluminum, and we're trying to find out what that temperature final would be if the temperature initial is at 150 degrees C. So this is your equation for your aluminum. Same thing for your water, which is the colder heat. You have Q cold equals MW, mass for the water, specific heat for the water. Its initial is 20 degrees C, and its final is what we're trying to find. So we know that Q hot is going to be less than 0 because this number is going to be lower than 150 degrees C, and the Q cold is going to be above 0 because this number is going to be greater than the 20 originally. So we have the total heat is the combination of both Q cold plus Q hot, so they should equal 0. But we know that they should also equal each other, even though we're going to lose heat on the aluminum pan. So we're able to equal each other out. So we have the water over here, and we have the aluminum over here. So now we can solve for TF. So there's different ways you can go about this. You can go ahead and multiply everything out if you would like that. So that means multiplying MWCW times TF and your 20 degrees, and same thing over here. Or you can try to transfer one to the other side, however you want to tackle this problem. But the end result should be M of the aluminum, specific heat of the aluminum, times your 150 degrees C, plus your mass of the water, times your specific heat of the water, times 20 degrees C, over mass of the aluminum, specific heat of the aluminum, plus mass of the water, and specific heat of the water. And you know all of these values on the right side. So after this, all you have to do is plug in. So once you multiply everything out and divide, you get that the final temperature is going to be 59.1 degrees C, which falls between 20 and 150 degrees C. So from that aspect, it makes sense. You know, the temperature should be between the hotter and the colder substance. If you were to get like something like 200 degrees C or 0 degrees C or whatever, something out of that range, then there was a miscalculation somewhere. And if you were to plug in that 59.1 back into these two respective equations, then you should see that the Q cold is going to be a positive number and the Q hot here is going to be a negative number. So that still follows these two rules that we put forth at the beginning. Okay, so now into phase changes. So far we have discussed temperature change due to heat transfer. No temperature change occurs from heat transfer if ice melts and becomes liquid water, i.e. during a phase change. For example, consider water dripping from icicles melting on a roof warmed by the sun. Conversely, water freezes in an ice tray cooled by lower temperature surroundings. So energy is required to melt a solid because the cohesive bonds between the molecules in the solid must be broken apart such that in the liquid, the molecules can move around at comparable kinetic energies. Thus, there is no rise in temperature. Similarly, energy is needed to vaporize a liquid because molecules in a liquid interact with each other via attractive forces. There is no temperature change until a phase change is complete. The temperature change of a cup of soda initially at 0 degrees C stays at 0 degrees C until all the ice has melted. Conversely, energy is released during freezing and condensation, usually in the form of thermal energy. Work is done by cohesive forces when molecules are brought together. The corresponding energy must be given off, dissipated, to allow them to stay together. So for here, we have from solids to liquids. If we are to get a solid to melt into a liquid, you see how the molecules here are bounded together, but once they melt, they're a little bit more free flowing. And then inversely, if we're trying to freeze a liquid into a solid, the molecules get more sturdy. And same thing here for liquid to gas. If we were to evaporate water, the gas would have more free flowing molecules versus the liquid. So in phase changes, there's a little bit of a difference in the formulas. The energy involved in a phase change depends on two major factors: the number and strength of bonds or force pairs. The number of bonds is proportionally to the number of molecules and thus the mass of the sample. The strength of forces depends on the type of molecules. The heat, Q, required to change the phase of a sample of mass is given by Q equals mLF, melting and freezing, or freezing, and Q equals mLV, vaporization or condensation. So LF is latent heat of fusion, and LV is latent heat of evaporation. So the graph here shows temperature versus energy added. So the system is constructed so that no vapor evaporates while ice warms to become liquid water, and so that vaporization occurs, the vapor remains in the system. The long stretches that of constant temperature values at 0 and 100 degrees C reflect the large latent heat of melting and vaporization respectively. So here, if ice heats up from -20 to 0, it will not heat any more until all the ice is melted. Once all the ice becomes water, liquid, then it'll be able to heat up to about 100. When there, it will start boiling and evaporating. And again, the entire liquid will not gain any more energy or any more temperature, until it becomes all steam. And then it'll increase in temperature again. So these parts right here are the phase changes. So for example, 14.4, 3 ice cubes are used to chill a soda at 20 degrees C with the mass of the soda being 0.25 kilograms. The ice is at 0 degrees C and each ice cube has a mass of 6 grams. Assume that the soda is kept in a foam container so that heat loss can be ignored. Assume the soda has the same heat capacity as water. So this is our specific heat for our soda. Find the final temperature when all the ice has melted. Okay, so we want a heat that equals the ice and the soda. But remember, one of these has to be negative because the total heat transfer should be 0. So initially we had Q ice plus Q soda equals 0, and we moved over that soda. So here we have the heat transfer to the ice for ice is the mass of the ice times its latent heat plus mass of the ice times the specific heat times the temperature change. The heat given off by the soda is Q soda equals mass of the soda, specific heat of water because we were told that we can use that one, and the temperature change. Since no heat is lost, we have that Q ice is equal to the negative Q soda. So again, we can equal them out to each other and solve for final temperature. The extra part here is that you have to include this part right here, the mass of the ice times its latent heat. So, but over here, again, we know everything on the right side. So we have our mass of the ice, we have 6 grams per ice cube, and we are told we have 3 ice cubes. So 3 times 6 grams, that equals to 0.018 kilograms, and the mass of the soda is 0.25 kilograms. So for the mass of the soda times its specific heat times its 20 degrees C, we have 20,930 joules. And for the phase change of ice, we have 0.018 kilograms times 334,000 joules times per kilograms, and that'll give us 6,012 joules. The denominator here, adding the mass of the soda and the mass of the ice times the specific heat, is 1,122. So we plug those in, and all they did here is just do each part separately. That's all we did. You get the final temperature is around 13 degrees C. That would be the temperature when everything is at equilibrium, all the ice has melted, and the soda is cooled down. So for figure 14.9, condensation forms on this glass of iced tea because the temperature of the nearby air is reduced to below the dew point. The air cannot hold as much water as it did at room temperature, so the water condenses. Energy is released when the water condenses, speeding the melting of the ice in the glass. So now heat transfer. What about methods by which heat transfer occurs? Whenever there is a temperature difference, heat transfer occurs. Heat transfer may occur rapidly or slowly, and we can control rates of heat transfer by choosing materials such as thick wool clothing, controlling air movement such as weather stripping around doors, or by choice of color such as white clothing to reflect summer. So many processes involve heat transfer. It is hard to imagine a situation where no heat transfer occurs. Yet every process involving heat transfer takes place only by these 3 methods. Conduction is a heat transfer through stationary matter by physical contact. The matter is stationary at a macroscopic scale. We know that there is a thermal motion of atoms and molecules at any temperature above absolute zero. Heat transfer between the electric burner of a stove and the bottom of the pan is transferred by conduction. So that's the physical contact. Convection is a macroscopic movement of fluid. This type of transfer takes place in a forced air furnace and in weather systems, for example. Heat transfer by radiation occurs when microwaves, infrared radiation, visible light, or another form of electromagnetic radiation is emitted or absorbed. An obvious example is warming of the earth by the sun. A less obvious example is thermal radiation from a human body. So here we have all 3 types of heat transfer. We have radiation coming in through the windows from the sun. We have convection flowing through here, from the room into the furnace here, and convection wherein all the hot air is rising. And then we also have conduction here, where we have the fireplace heating up physically because they're in contact this part of the region. So for conduction, insulation is used to limit the conduction of heat from inside to the outside in the winters and outside to the inside in the summer. The molecules in 2 bodies at different temperatures have different average kinetic energies. Collisions occurring at the contact surface tend to transfer energy from high temperature regions to low temperature regions. In this illustration, a molecule in the lower temperature region on the right side has low energy before collision, but its energy increases after colliding with the contact surface, right here in the middle. In contrast, a molecule in the higher temperature region on the left side has high energy before collision, but its energy decreases after colliding with the contact surface. And that's pretty much every single example we've noticed up until now. In general, good conductors of electricity, metals like aluminum, copper, gold, and silver, are good conductors of heat, and insulators of electricity, wood, plastic, and rubber, are poor conductors of heat. Some materials conduct thermal energy faster than others. The previous figure shows molecules in 2 bodies at different temperatures. The average kinetic energy of a molecule in a hot body is higher than in the colder body. If two molecules collide, an energy transfer from the molecule with the greater kinetic energy to the molecule with the less kinetic energy occurs. The cumulative effect from all collisions result in a net flux of heat from the hot body to the colder body. The heat flux thus depends on the temperature difference delta T from T hot minus T cold. Therefore, you will get a more severe burn from boiling water than from hot tap water. Conversely, if the temperatures are the same, then the heat transfer rate falls to zero and equilibrium is achieved. Owing to the fact that the number of collisions increases with increasing area, heat conduction depends on the cross-sectional area. If you touch a cold wall with your palm, your hand cools faster than if you just touch it with your fingertip. So again, here's a hotter surface over here and a colder surface over here. So heat conduction occurs to any material represented here by a rectangular bar, whether window glass or walrus blubber. The temperature of the material is T2 over here on the left and T1 on the right, where T2 is greater than T1. The rate of heat transfer by conduction is directly proportional to the surface area, A. So this little surface area right here. The temperature difference, T2 minus T1, and the substance's conductivity, K. The rate of heat transfer is inversely proportional to the thickness D. So the thickness between here. Conduction, a third factor in the mechanism of conduction, is the thickness of the material through which heat transfers. The previous figure shows a slab of material with different temperatures on either side. Heat transfer from the left side to the right side is accomplished by a series of molecular collisions. The thicker the material, the more time it takes to transfer the same amount of heat. This model explains why thick clothing is warmer than thin clothing in the winters, and why Arctic mammals protect themselves with thick blubber. Lastly, the heat transfer rate depends on the material properties described by the coefficient of thermal conductivity. All four factors are included in a simple equation that was deduced from and is confirmed by experiments. The rate of conductive heat transfer through a slab of material is given by Q over T equals K, which is the constant, your surface area A, the change in temperature T2 minus T1, over your thickness, where Q over T is the rate of heat transfer in watts or kilocalories per second, K is the thermal conductivity of the material, A and D are its surface area and its thickness, as seen in the previous figure, and T2 minus T1 is temperature change. So for example, 14.5, we have a styrofoam ice box, has a total area of 0.95 meters squared, and the walls with an average thickness of 2.5 centimeters. The box contains ice, water, and canned beverages at 0 degrees C. The inside of the box is kept cold by melting ice. How much ice melts in one day if the ice box is kept in the trunk of a car at 35 degrees C? So here we have our A already, right? 0.95 meters squared. Our D, which is 2.5 centimeters, that turns into 0.025 meters. Our temperature 1, which is starting off the icebox at 0. Our temperature 2, which is 35. We want to know a day, so that turns into 24 hours, which turns into 86,400 seconds. And we are solving for M, right? So we know we have to use this equation here that we just learned. But our Q here, we have to have the ice melt. So we have the known values here. We have our 0.01. We have our surface area. This is K. This is our surface area. Our change in temperature over the thickness. So Q over T equals 13.3 joules per second, right? So we also have our time that goes down here. So that'll give us 1.15 times 10 to the 6th joules, right? So this is what our Q equals. So set this equals to heat transferred of the ice. So you're going to use the 1.15 we just found out because this is the rate of change. This is our heat transfer rate. So mass equals Q over LF. We just found this number out, and this is a given. So we get 3.44 kilograms of ice. So around 7.6 pounds seems to be about right based on experience. You might expect to use about 4 kilograms of bag of ice per day. A little extra is required if you add any warm food or beverages. So we have convection. This is driven by large-scale flow of matter. In the case of the Earth, the atmospheric circulation is caused by the flow of hot air from the tropics to the poles and the flow of cold air from the poles to the tropics. Note that Earth's rotation causes the observed easterly flow of air in the northern hemisphere. Car engines are kept cool by the flow of air in the cooling system, with the water pump maintaining a flow of cool water to the pistons. The circulatory system is used in the body when the body overheats, the blood vessels in the skin expand, they dilate, which increases the blood flow to the skin where it can be cooled by sweating. These vessels become smaller when it is cold outside and larger when it's hotter. So more fluids flows and more energy is transferred. The body also loses a significant fraction of its heat through the breathing process. While convection is usually more complicated than conduction, we can describe convection and do some straightforward, realistic calculations of its effects. Natural convection is driven by buoyant forces, with hot air rising because density decreases as temperature increases. Ocean currents and large-scale atmospheric circulation transfer energy from one part of the globe to another. Both examples are natural convection. So here you have air being heated by the so-called gravity furnace, expands and rises. So hot air rises here. It gets to a point where it cools back down, and it's just a cycle, forming a convective loop that transfers energy to other parts of the room. As the air is cooled by the ceiling and outside walls, it contracts, eventually becomes denser than room air, and sinking to the floor. A properly designed heating system, usually using natural convection like this one, can be quite efficient in uniformly heating a room. Convection plays an important role in heat transfer inside this pot of water. Once conducted to the inside, heat transfer to other parts of the pot is mostly by convection. The hotter water expands, decreases in density, and rises to transfer heat to other regions of the water, while colder water sinks to the bottom. This process keeps repeating. So why do animals have fur? The amount of available space for airflow determines whether air can induce convection. The space between the inside and outside walls of a house, for example, is about 9 centimeters, large enough for convection to work effectively. The addition of wall insulation prevents airflow, so heat loss or gain is decreased. Fur, fiber, and fiberglass also take advantage of this by trapping air in spaces too small to support convection, as shown in the figure. Fur and feathers are lightweight and thus ideal for the protection of animals. Fur is filled with air, breaking it up into small pockets. Convection is very slow here because the loops are so small. This makes fur a good lightweight insulator. An important example of the combination of phase change and convection occurs when water evaporates from the oceans. Heat is removed from the ocean when water evaporates. If the water vapor condenses in liquid droplets as clouds form, heat is released in the atmosphere. Thus, there is an overall transfer of heat from the ocean to the atmosphere. This process is the driving power behind thunderheads, those great cumulus clouds that rise as much as 20 kilometers into the stratosphere. Water vapor carried in by convection condenses, releasing tremendous amounts of energy. This energy causes the air to expand and rise when it is cooler. More condensation occurs in these colder regions, which in turn drives the cloud even higher. Such a mechanism is called positive feedback, since the process reinforces and accelerates itself. These systems sometimes produce violent storms with lightning and hail and constitute the mechanism driving hurricanes. So, last one is radiation, radiative heat transfer. Most of the heat transfer from this fire to the observers is through infrared radiation. The visible light, although dramatic, transfers relatively little thermal energy. Convection transfers energy away from the observers as hot air rises, while conduction is negligibly slow here. Skin is very sensitive to infrared radiation so that you can sense the presence of fire without looking at it. You can feel the heat transfer from a fire and from the sun. Similarly, you can sometimes tell that an oven is hot without touching its door or looking inside. It may just be warm as you walk by it. The space between the Earth and the Sun is largely empty without any possibility of heat transfer by convection or conduction. In these examples, heat transfer is radiation. That is, the hot body emits electromagnetic waves that are absorbed by our skin. No medium is required for electromagnetic waves to propagate. Different names are used for electromagnetic waves at different wavelengths: radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X rays, and gamma rays. The energy of electromagnetic radiation depends on the wavelength, the color, and varies over a wide range. A small wavelength or a higher frequency corresponds to a high energy. Because more heat is radiated at higher temperatures, a temperature change is accompanied by a color change. Take, for example, an electrical element on a stove, which glows from red to orange, while the higher temperature steel in a blast furnace glows from yellow to white. The radiation you feel is mostly infrared, which corresponds to a lower temperature than that of an electrical element and the steel. The radiated energy depends on its intensity, which is represented in the figure below by the height of the distribution. All objects absorb and emit electromagnetic radiation. The rate of heat transfer by radiation is largely determined by the color of the object. Black is the most effective and white is the least effective. People living in hot climates generally avoid wearing black clothing, for instance. Similarly, black asphalt in a parking lot will be hotter than adjacent gray sidewalk on a summer day because black absorbs better than gray. The reverse is also true. Black radiates better than gray. Thus, on a clear summer night, the asphalt will be cooler than the gray sidewalk because black radiates the energy more rapidly than gray. An ideal radiator is the same color as an ideal absorber and captures all the radiation that falls on it. In contrast, white is a poor absorber and is also a poor radiator. A white object reflects all radiation like a mirror. A perfect polished white surface is a mirror like in appearance, and a crushed mirror looks white. So for figure 14.24, you have for A, a graph of the spectra of electromagnetic waves emitted from an ideal radiator at three different temperatures. The intensity or rate of the radiation emission increases dramatically with temperature, and the spectrum shifts towards the visible and ultraviolet parts of the spectrum. The shaded region denotes the visible part of the spectrum. It is apparent that a shift towards the ultraviolet with temperature makes the visible appearance shift from red to white to blue as the temperature increases. So a visible figure would be here. Note that the variations in color correspond to the variations in flame temperature. So the hotter part is down here, closer to the point of contact, and the cooler part of this flame is up here when it's red and a little bit orange. This illustration shows that the darker pavement is hotter than the lighter pavement. Much more of the ice on the right has melted, although both have been in the sunlight for the same amount of time. The thermal conductivities of the pavement are the same. The rate of heat transfer emitted by radiation is determined by the Stefan-Boltzmann law of radiation. Q over T equals these two variables, a, t to the fourth, where this one equals 5.67 times 10 to the negative 8, and this is Boltzmann's constant, Stefan Boltzmann's constant. A is the surface of the object, and T is the absolute temperature in Kelvin. The symbol E stands for emissivity of the object, which is a measure of how well it radiates. An ideal jet black or black body radiator is E equals 1, whereas a perfect reflector has an E equals 0. Real objects fall between these two values. Take, for example, Tutson's light bulb filaments, which have an E of about 0.5, and carbon black, a material used in printer toner, which has the greatest known emissivity of 0.99. The radiation rate is directly proportional to the fourth power of the absolute temperature, a remarkably strong temperature dependence. Furthermore, the radiated heat is proportional to the surface area of the object. If you knock apart the coals of the fire, there is a noticeable increase in radiation due to the increase in radiating surface area. So for here, we have figure 14.27. A thermograph of part of the building shows temperature variations, indicating where heat transfer to the outside is most severe. When is our major region of heat transfer to the outside of the homes? So for example 14.9, what is the rate of heat transfer by radiation with an unclothed person standing in a dark room whose ambient temperature is 22 degrees C? The person has a normal skin temperature of 33 degrees C and a surface area of 1.5 meters squared. The emissivity of skin is 0.97 in infrared, where the radiation takes place. Okay, so insert values for T2, which is 295 Kelvin, and T1 for 306 Kelvin. Remember, it's got to be absolute temperature here. So you plug in all your constants and your variables here. We know our surface area. We know both of our temperatures. It gave us E. So here we get negative 99 joules per second, which is negative 99 watts. So figure 14.28, the greenhouse effect is a name given to the trapping of energy in the Earth's atmosphere by a process similar to that used in greenhouses. The atmosphere, like window glass, is transparent to incoming visible radiation and most of the sun's infrared. These wavelengths are absorbed by the sun and re-emit as infrared. Since Earth's temperature is much lower than that of the sun, the infrared radiated by the Earth has a longer wavelength. The atmosphere, like glass, traps those longer infrared rays, keeping the Earth warmer than it would otherwise. The amount of trapping depends on concentrations of trace gases like carbon dioxide, and a change in concentration of these gases is believed to affect the Earth's surface temperature. So for here, this simple but effective solar cooker uses the greenhouse effect and reflective material to trap the retained solar energy. Made of inexpensive durable materials, it saves money and labor and is of particular economic value in energy-poor developing countries. And that will do it for chapter 14.